Okay, so this video is going to give the theory around implicit differentiation. It is difficult, so you might have to pause it at different points to kind of understand what is going on. Okay, so this is kind of related, I suppose, to the thing when someone talks about the equation of a line. What does it mean to say that a line has an equation? Do you understand what that means? Is that not a bit... What does it mean to say that a line has an equation? So we're going to explain exactly what that means. So this is to be set up as, suppose you have some formula in x and y equal to 0. Now often when we write these, for example here, x squared plus y squared equal to 16, you say, oh, that's equal to 16. Well, take away the 16 from both sides and you've got some formula in x and y, x squared plus y squared minus 16 equal to 0. Or here, take away the 2x plus 3 from both sides, you get y minus 2x minus 3 is equal to 0. So the thing is, when you write down an equation in x and y, what you can actually do is you can go away and the equations give you curves. Now I need to explain exactly how they give curves, and I'm just, excuse me there a second, I'm just grabbing my compass. So basically what you have is that equations have solutions, and equations like this, the solution is a pair, an x value together with a y value, and if you plot them as a coordinate and you plot all the solutions, you get a curve. So for example, y equal to 2x plus 3. Now what I'm going to do initially with y equal to 2x plus 3 is I'm actually just going to draw it first and then kind of explain what's going on. So y equal to 2x plus 3, okay, I'm going to just put one point here, 0, 3. This will not be to scale. Draw a straight line. Okay, and I'm also going to draw a circle. Now, why is this a line and why is this a circle? Well, they're kind of harder questions. What you can show with the line is that if you take any two solutions of this, so for example 0, 3 and 1, 5 I think are both solutions. We'll look at this in a minute. If you take any two solutions on that, so any 2 points on the curve, so points on the curve correspond with solutions of the equation. So maybe I need to write that down the bottom. Points on curve correspond exactly to solutions of equation. So for example, 2x plus 3, maybe just take my word that if you plot all the solutions of this equation you get a straight line. So for example 0, 3, the y coordinate is 3, it's equal to twice the x coordinate, twice 0 plus 3. So 0, 3 is a solution of the equation, 0, 3 is a point on the curve. And then we might come over to here, for example, where we'll just go up here and say get the point 7, and well, I'm going to find the y that makes it work. So the y should be twice the x, that's 14, plus 3 is 17. And as you plot all the solutions to this particular equation, you get a line. And what you can show is that if you take any two of them, that the slope between them is the same. It'll be equal to the rise over the run. So for example here, the rise is 3 to 17 is 14, and the run is 0 to 7 is 7. 14 over 7 is 2, and that's what this is. This is where it cuts, and this is the slope. Okay. Another example is x squared plus y squared is equal to 16. We'll just put some points here. So for example, 4 along the x, 0 along the y, and let's say 0 along the x minus 4 along the y. So let's look at x squared plus y squared. You get 4 squared plus 0 squared. 16 plus 0 is equal to 16. This is a solution of the equation, so it is a point on the curve. Similar story with 0 minus 4. Where does this equation come from? Well, what you do is you say, okay, look at how this is made. Take all the coordinates whose distance from 0, 0 is equal to 4. And if you write down that equation, if you write that down, you get x squared plus y squared equals 16. We might see that a little bit later. Okay, now, what this means for us is that when you write down an equation, you get a curve. Well, maybe these curves are smooth, maybe they have tangents. For example, looking at this point, this looks to be smooth. If I zoom in on it, it looks like a straight line. What is the straight line it looks like? We call it the tangent. And what this section is about is if you have these, what these things are called implicit curves. Now, the implicit, as far as I'm concerned, is the following. If you write down a little equation like x squared plus y squared equals 16, it doesn't really mean anything necessarily. But these implicit curves, the idea is it's not explicitly said, but when you write this down, the idea is that, oh, we're talking about a curve. So this is the bit that is implicit in this implicit curve, would be my understanding. Okay, so let's look in particular again at, say, the circle. So an equation x squared plus y squared equal to 1 is the equation of the unit circle. We'll probably see this in the next video in the examples. So this is the equation of the unit circle. Now, so you get these curves, and these are kind of simple curves. We'll see more complicated ones in a second, in the examples video. So these curves, like circles, are smooth if you zoom in on a particular point. So for example, if we look at 1 over root 3, root 2 over 3, which might be something like this point here. 1 over root 3, 2 over root 3. So if you look at this point and zoom in, now I won't adjust my zoom because I haven't got this in front of me, but I suppose I can bring it up. Nah, it's silly. Just look in between my fingers at the point, and as you get closer and closer and closer, it looks like a straight line. The straight line that it looks like is what we call a tangent. So basically what I'm trying to eventually say is that many of these implicit curves are smooth, they have tangents, and we might be interested in finding the slope of their tangents. This is what we're getting at. Now, you might look at these curves like a circle and say, okay, well, why don't I just differentiate it like I did last semester? The reason you can't do that is because these implicit curves are not the graph of a function. Remember, a function is something that you put a number in and you get a number out. Now, if this was the graph of a function, well, you always plot the inputs along the x. Now, I won't write it but these would be the inputs and the y's are the outputs. And if you take the input 0, well, you're getting two outputs, minus 1 out and 1 out. And basically the theory here is that, well, not the theory, but what is actually going on here is that this is not the graph of a function, it's two different functions. And actually I can write down what they are. This top one, f1 of x, and it's the top semicircle. It goes the whole way around. Don't know why I was sparing the ink. So this is f1 of x, and you can show that this is plus the square root of 1 minus x squared. The bottom function, meanwhile, is minus it. So this is f2 of x is minus square root of 1 minus x squared. Now what you could decide to do is you could say, okay, if I've got an implicitly defined curve, what I'll do is I'll find, these are called branches. What branch of the curve is it on? Oh, and I'll go and find the formula for the function there, and then I'll just differentiate this like I did last semester. The unfortunate thing is there can be loads of different branches, and you cannot find the equation for it, and that happens in lots of examples. So this isn't what we're going to do. So instead what we're going to do is we're going to do something called implicit differentiation. We're going to do something similar to what we did in the first section, there's a big theorem, it's called, I think, the implicit function theorem, that says if you've got a smooth curve, and the parametric curves are often smooth, and these implicit curves are often smooth, what you can do is you can say, okay, if you zoom in on a particular point and you get within a neighborhood of a point, now what that means is just close enough to it. Now what you have to avoid, like the previous section, or not the previous section, but the first section here, is you avoid bits like this. This is a vertical tangent, the slope is undefined. You need to stay away from these bits, but as long as you stay away from these bits. Now you can extend much further, like here you can extend from x equal to -1 to x equal to 1, and that's local enough, that's a neighborhood of this point. And the big theory is that when you got a smooth curve, any type of smooth curve, that there is a function, that y is a function of x. And here you can see it explicitly, you can write it down, but most of the time you can't. Now here I'm going to just restrict a bit closer. So you got a smooth curve, it doesn't have jaggedy edges, it doesn't have jumps. The theory says in this region the y is a function of x, and what that means is there's some function that this is the graph of in that little interval. Okay, and this is what we're going to do with implicit differentiation. When we see an equation like x squared plus y squared equal to 1, what we're going to do, so x squared plus y squared equal to 1, we're going to say, okay, now actually, as it happens, this is kind of like, I mean, this is hard enough stuff that we're doing, there's no two ways about it, and maybe it's difficult to go through the thought process every time. You know, I mean, what's going on? You got an equation x and y, you replace the y with y of x. If you could do that, I'm delighted. Like, that's what you'll kind of have to do. Why the hell are you doing this? It's because of the theory. So I suppose it's a balance between being able to do the questions and understanding the theory. You see, if you try and understand the theory and you can't do any questions. But then on the other hand, when you try and do questions without understanding the theory, there's more to remember. Whereas for me, there's nothing really to remember here. I understand the theory that when you got this smooth curve near a particular point, the y is a function of x. And the idea then is that you can just differentiate this away without finding the formula for y of x. Now you never find what y of x is, but you can say what its derivative is. Its derivative is dy dx. So we'll see this in the next page. So what actually happens is, okay, you've got some curve, which I can write as some formula in x and y equal to 0. And what happens when you differentiate it? Say, for example, you differentiate x squared, you get some x's. If you differentiate y squared, we're going to see this on the next page, you're going to get, or in the next lecture, you're going to get some y's. But because of the chain rule, so to differentiate this y squared, differentiating the outside, you get, say, so the outside function here is x squared. Differentiate that, you get 2x. The chain rule says evaluate the inside, that's the y. So that's where the 2y comes from. So when you differentiate both sides of an equation like this, you get y's. But then you must multiply, according to the chain rule, by the derivative of what's inside, and the derivative of y of x is dy dx. Now what I'm writing down here is, if you've got a formula in x and y equal to 0, or now the 1 doesn't matter, it can just be a constant, differentiate both sides with respect to x, you end up with a formula with x, y, dy dx, and I think possibly always, I'm not actually sure, I'd imagine always, because you will always be able to solve this for dy dx. Now the thing that's different to before, if you differentiate this function here, it'll be in terms of x, and the derivative of this will be in terms of x. But when you do it with implicit functions, you don't know which one it is. So the derivative, it's not going to just have x, it's also going to have y, to distinguish between y equal to 1, this branch, and y equal to -1, this branch. Okay. Now the things to remember, the most important thing is that the derivative of y of x is dy dx. Now that's tautological, which basically is saying black is kind of all it's saying, but that's all it is. if you've got a function of y, you must use the chain rule. Now we will see this in examples, but it's like differentiating y of x, but let's write it down abstractly. If you were differentiating some function of y and this is, so some people actually, and including myself probably when I was younger, I wouldn't actually write this y of x, I would just remember it in my head. But there's an advantage to, especially when we see the next section, there's an advantage to writing the y of x because it makes the chain rules easier to see. You got a clear outside and a clear inside. So I recommend doing this. The chain rule says you differentiate the outside. The chain rule says you evaluate at the inside. Now you don't have to write the y of x every time, just once. So when I'm evaluating at the inside, I don't have to write y of x, I can just write y. But then you must multiply by the derivative of what's inside, and the derivative of y of x is dy dx. All other rules of differentiation apply as normal. So this is going to be difficult. The theory is difficult. The theory is covered. What we're going to be doing in our examples is we've got an equation in x and y. We're going to recognize that the y is a function of x. This is so-called locally. So I replace the y with y of x. That's the first thing. I do that actually at the very start. Then I differentiate both sides of this equation with respect to x, and I get a relationship between x, y, and dy dx, and I solve this for dy dx. I have to be careful with the chain rule, differentiating stuff like y squared, etc. So we'll see that in the next video.